So today we've got a kick-off with a talk from Sam Burns with his talk, Let's Go Quantum. Sam's an enthusiastic reader of cryptography specifications and is currently a senior software engineer at UpMind, so please give the man a big hand.
Good morning, everybody. Thanks very much for coming along this early in the morning. I hope you all had a good night last night, and well done for making it in. I hope everybody's enjoying the conference so far. It looks like a fantastic lineup. So this is my talk, Let's Go Quantum. So my name's Sam Burns. My interests are development, software architecture, information security. When I'm not doing that, I like to go climbing to make my fingers stronger so I can type faster. There's some links on the board. So the link to the blog, the slides are going up on that website probably tomorrow-ish. So if you like a copy of the slides, you can get them from there. There's some social media links. Wouldn't really say I'm that chatty, but you can follow me if you really want to. And there's a link to my LinkedIn there as well. Now, what we're going to be talking about today is, I'm just very quickly going to go over what the core concept of the talk is. Then we'll take more of a look at the background to quantum computing and what the current state of the art is. We'll talk about how you can simulate quantum computers in Go, if you want to, on a laptop. Then we're going to talk about post-quantum cryptography in general. We're going to address what it is, why we need it, and why we need it sooner than you think. And then I'll go over the features that were released in Go 123. Now, breaking news, it's obviously been a very exciting week for a couple of reasons. First of all, Go 123 was released 3 days ago. Round of applause for the Go team. Thanks very much for all the free stuff. So this happened on Tuesday, the 12th of August, which is obviously 3 days ago. So I had to rewrite my talk. Now, there are some examples in the slides that were compiled and run with Go 123 release candidate 2, but I've been over everything that's changed in the finalized version, and basically it doesn't really affect anything that's going to be on the slides, fortunately. And then just when I'd finished rewriting the talk on Tuesday, an important standards body called NIST finalized a standard that we've been waiting for well over a year now. So NIST they had a group of candidates of possible quantum cryptography algorithms that they might be recommending, and the final recommendations came out on Tuesday. Now, there's a lot to be said about what they are, but if you remember nothing else, remember this: Go 123's implementation offers the same level of security as the finalized version of the cryptographic standard, even though it was released on the same day as the finalized version. There are some tweaks that are being suggested, but they don't affect the security of Go 123, and you can and should be using the crypto provided in the TLS package. So the talk's been rewritten twice in the last couple of days, but at least you're getting up-to-date information at GopherCon UK. You know, you get your money's worth at this conference. Okay, so the core concept is basically quantum computers exist. They're not great now, but one day they will be able to break our encryption. This means that we need new encryption, starting with TLS. We're going to have a look at why that's the most important area and why these changes have to happen sooner than you think. So a common question that gets asked is, why is this being added so soon to Go? We'll talk about why that is. And we're starting to get new cryptography starting from Go version 123. So, having looked at the core concept, let's take a look at what quantum computers actually are. Quantum computing is using the complexity of quantum mechanics to perform calculations. If predicting the outcome of an experiment is very computationally complex, then to perform that experiment is to get the answer to a very complex calculation quickly. Quantum computers do exist. They're quite new. They're in their infancy. You can rent time on a quantum computer via a cloud provider now. Some of them even have free tier offerings. We'll be talking about that later if you'd like to have a go at running an actual quantum algorithm, which is pretty cool. Sadly, we won't be doing that today. I wasn't quite brave enough to do a live coding demo on a quantum computer, but it can be done. It can be done. No, we'll show you how. And in terms of applications, essentially we don't know. We know that there will be applications in cryptanalysis. It's possible that quantum physics simulations, fluid dynamics, and drug design might be areas where these things are useful, but the reality is much like the invention of the silicon chip. We've got this cool thing, but we don't yet know everything we're going to use it for. So, quantum mechanics magic is something that I don't really understand. Even if I did, wouldn't be able to explain it in an hour. So, there are a few interpretations, the Copenhagen interpretation, the many worlds theory of quantum mechanics phenomena. None of them are really any good to us, because what we need is, first of all, as I say, an interpretation that I can understand, and secondly, one that I can explain in less than an hour. So, the one we're going with is that there's a magic wizard that does cool stuff to subatomic particles, and that's the interpretation that I can now unveil here, and we will be using this throughout the talk. Okay, so, and if you promise to believe me, I promise to finish on time. Now, moving on. Quick note about image credits. There's a lovely gentleman named Juan de la Cruz Garcia, who has been using PenPot to create some images, one of which is a realistic diagram of an electron, which he's created for us, so we can use this to talk about subatomic particles. Electrons have spin. This is another one of those areas where a little white lie is much faster than the truth, so they are literally spinning, promise. It can spin in two different directions. We, as computer scientists, can label things with a 0 and a 1 if we want to, so excuse me, I do beg your pardon. So we'll be calling the two different directions that this electron can spin, 0 and 1. To make it look cooler, we're going to put little pointy things around the numbers. That's called a ket from linear algebra notation. So this is an electron spinning. Thank you to Señor de la Cruz Garcia for providing the images. What's happening with this electron is it's spinning in the upwards direction, so we can say that that represents a 1 if we want to. This one spins in the downwards direction. But the interesting thing about electrons is if you have a laser, and as it happens, because I'm presenting, I actually do, what you can do if you fire an electron at a laser, like that, is that you can make it spin in both directions at the same time. So we now have this model of a subatomic particle which can have two contradictory properties at the same time. We're going to call this a quantum superposition, and we've labelled it with ket psi because putting Greek letters on the slides makes me look cleverer than I am. So, moving on to what this means. In engineering terms, we can do stuff with this. There's a thing called a qubit. A qubit is a quantum bit. This is generically any subatomic particle with some binary property that's subject to quantum phenomena. So it doesn't have to be an electron. We've used one as an example, but any subatomic particle that can be doing two opposite things at once under the careful control of a magic wizard can be thought of as a qubit if we can harness its power and use it for computation. Unlike classical bits, which represent a 0 or a 1, a qubit represents both by varying probabilities. We've expressed the state of the qubit as ket psi equals alpha ket 0 plus beta ket 1. Again, it's an area where it's slightly faster to lie than it is to tell the truth, but alpha and beta are probabilities. Sort of. There's a little bit more complexity than that, but essentially what we're expressing here is that the state of this quantum superposition is two contradictory things at the same time by two different probabilities, kind of. Now, it's useful when reasoning about how these things work to sometimes to represent them in a particular kind of diagram. If you decide to go and read more about this, you might see this thing called a Bloch sphere. which is that little globe there. So what we've done is we've drawn an arrow, which is a vector, that represents the actual state of our qubit, and the polar values are a 1 and a 0. So that's what the qubit would look like. Or that's what position the qubit would be in if it represented actually a 1 or a 0. If it's pointing anywhere else, there's more information there, but it's basically probabilistically both by slightly different margins. So it's useful when reasoning about quantum algorithms, what quantum gates do, to imagine the qubit as this data structure that can be visually represented as a sphere in a three-dimensional vector space with an arrow going from the center to somewhere on its surface. And when you do stuff to a qubit, you're moving the arrow basically. So that's our representation of a data structure here. It's not a 0 or 1, it's something more complicated. There are different physical implementations, as I say. We'll go over some of them later, but there's a system called trapped ions. You can also do something cool with superconductors, which we'll be talking about. There are different physical implementations, but you can run the same kind of quantum algorithms on any of them. So this is sort of analogous to, in classical computing, Turing machines. We've seen actual implementations which use silicon wafers or which use vacuum tubes. There's different physical implementations, but you can run the same kind of code on them, basically. Now, measuring a qubit is a very complicated topic because they're quite small and fiddly, but if you'd like a sensible answer about how you do that, there are books available. There's one called Quantum Computing and Quantum Information by Mike and Ike, which is quite popular. My only criticism of it was there weren't enough memes in it. So this is what happens when you measure a qubit. Okay. When the state of a qubit is unobserved, we can describe the state as being ket psi equals alpha ket 0 plus beta ket 1, which means the state of the qubit is some probability of being a 0 and some probability of being a 1. When you look at it, however, it snaps to a binary value. In fact, if anything touches the qubit, it does what's called quantum decoherence. So it snaps to a 1 or a 0 suddenly, and measuring it counts as touching it. So we have here a diagram of deliberate quantum decoherence through measurement. It can also happen by accident, but more on that later. Now, what can one do with a qubit? Well, the first thing you can do is you can apply transformations that twist or flip the data structure, the vector space, pushing the qubit, the vector, to a new value. So basically, you do a mathsy operation on it that has linear algebra in it, and that makes the arrow move. If anything touches a qubit, its value becomes 0 or 1, measuring it counts as touching it. As a developer, that's not very satisfactory. It's quite hard to write code if when you try to read a variable, it just gives you a random number. Fortunately, one of the transformations that you can do on the state of a qubit is called an amplitude amplification. So one important thing to realize is one of the operations that you could do to it has the effect of moving the arrow closer to whichever pole it was really close to begin with. So that's called amplitude amplification. It amplifies the probability of you getting whatever was the most likely value. So then when you interrogate the state of your qubit, you still don't actually get to find out where the arrow was, but you do get to find out which hemisphere it was in. So you can get some information out of it, if not as much as we would normally like. So, how do you manipulate a qubit? Well, the answer is quantum logic gates. Much as those of you who've done a computer science degree will at some point have drawn diagrams of logic gates and then expressed them as code. You can do the same thing with qubits too. In fact, your early experiments in coding on a quantum computer will feel a lot like circuit design. Realizing this helps to bridge the gap between what a qubit is and what a quantum algorithm is. Even though, you know, in much the same way, it would be fair to say that showing somebody some logic gates doesn't really explain what object orientation is. I'm aware that there's a little bit of a gap between the different levels of abstraction here, but we'll do the best we can with the output we've got. So there are an unlimited number of possible quantum gates. It's not like classical logic gates, where, for example, a NOT gate is a unary gate. It has one input, one output. There's only really one sensible thing it can do, which is to flip it. with qubits because there's essentially an unlimited number of possible values they could have. That means there's an unlimited number of useful operations you can do on them. So even amongst unary operators, in theory, there isn't sort of a limit as to how many there are, but there are some well-known ones. And part of their power is that they can do some quite complex maths. We've got a couple of examples on the screen here, but it's not really necessary to go around memorizing them all. But the core concept is that when we design a circuit, we're representing a quantum gate, and that quantum gate has some effect on the value of a qubit. They're all a little bit different. And for simplicity, we're only working with real numbers on the screen, but the truth is these are complex numbers, so the way that the probabilities are expressed, these amplitudes have imaginary number components to them as well, just to make things a little more complicated. Now, quantum entanglement means linking two or more qubits by magic, because a wizard does it. Influencing one qubit infects the entangled group. Measuring one collapses its wave function, so it becomes a 1 or a 0, but so do any other qubits to which it's been entangled. So when you create a quantum entanglement, you have a system of multiple qubits, which between them can be in a superposition of a number of different possible states at the same time. And when you act on one, you're essentially acting on all of them. So n entangled qubits can represent a superposition of 2 to the power of n states. Again, slight oversimplification and a little white lie that's faster than the truth. But that basically gives you an idea of where this idea of parallelism is coming from. So we can often think of a quantum computer as having a parallel processing capability that's fundamentally different from silicon trips. The implications of entanglement are where the power of quantum computing really lies. Parallelism breaks down the normal relationship between the size of a problem and how long it takes to solve it. For example, and we will be going over the relevance of this one to cryptography, if the problem you're trying to solve is expressing a number as the product of prime factors, it's not just a case that quantum computers can do it faster, it's that the relationship between the size of the numbers and the number of steps that have to be performed is fundamentally different. They're not just running the same algorithm faster, they're running a completely different kind of algorithm. So, quantum decoherence effect. This is when quantum computers go bad. So if there's any metaphorical grit in the machine, any background radiation, anything like that, touching a qubit, that sort of makes it break. One thing we can do about that is there's this concept of quantum error correction. So this is the idea that a number of physical qubits together can form one logical qubit. Some of the easiest examples to understand use what are called 8 ancilli qubits and one data qubit, which sort of gets fixed if something breaks. But you often need more than one shot to get your code to work. So you might, if you write quite a large algorithm and try to run it on a large quantum computer, find that something's simply gone wrong and you have to run it again. Now, in practice, the number of physical qubits there are to a logical qubit varies a lot depending on the hardware implementation. But there are things that we can do about it because this is an area where the mechanics is a little fiddly and it is difficult to get things to the right temperature and keep radiation out. Now, excuse me, I'm slowly losing my voice while I'm talking. We'll see if I can keep going for another half an hour. So, different hardware implementations of quantum computers exist. Some of these are, for example, there's a company called IonQ that offers a quantum computing service using trapped ions, which is where a little atom is kept prisoner between some magnets for some reason. Photonics, there's a company called Xanadu, for example, who do what, as far as I've been able to gather, is something cool with laser guns. And superconductors. So IBM's quantum offerings, there's one there. The picture's actually being cropped. That's actually the cooling system. So that's like the bit of the bit on the back of your fridge. So the way the superconductors work is you make a little circuit, a very tiny one, with no electrical resistance whatsoever, create an electrical circuit, unplug the battery because there isn't any resistance, it keeps spinning. This only works when it's really chilly in there. And until you check which direction your current is going, clockwise, anti-clockwise, the answer is kind of both at the same time. And you can entangle them because they have an electromagnetic influence on other such circuits. So you can actually run code on IBM computers using this system. If you've never run your code at absolute zero before, give it a go. Now, in terms of the software ecosystem, the main tool is Qiskit. This is a simulator. It's probably a good place to start learning. It's got some of the best learning resources available, and there's also some tools in there for assisted circuit design and optimization that helps you actually essentially write your quantum algorithms. There's a standard called OpenQASM, which is a sort of communication standard for talking to quantum computers. This integrates with Qiskit. Google have an offering called Cirq, similar to Qiskit. It's another similar library that lets you both simulate quantum computers and integrate with actual quantum hardware. Excuse me. I do beg your pardon. TensorFlow. This is a product which is mostly about QML stuff, so quantum machine learning. It's a field of research that does exist. I'm not sure we're yet at the point where it's better than normal classical architecture machine learning, but maybe one day. And there's the Q# language, which is, imagine if C# met Python and then started talking to quantum hardware. That's what it's like. In fact, as a matter of fact, most of this stuff is written in Python. Qiskit is a Python library. So if anybody would like to see if we can build up a better Go ecosystem for working with this stuff, do feel free. So the IBM free tier that I talked about, you get 10 minutes of execution time a month on a real quantum computer. You can also run the simulator locally on your own hardware. I think it's still true that the machine that IBM are offering for their free tier has 127 qubits or something like that. IonQ, you can use the Azure credit system, the corporate pricing's available. And there are other companies, of course, Xanadu and D-Wave, that have quantum computing offerings. But as I say, you are going to have to write some Python at some point. However, we don't want to do that, we want to write Go. So let's take a quick look at how we can simulate quantum computers in Go. And thankfully, some kind person has written a library that lets us do that. So this GitHub library here is a project that's been thanklessly maintained for a number of years by one contributor, simulating quantum computing in Go in a world that's decided to use Python. The simulator provides 20 different logic gates. So your circuit diagram, you've got 20 different options to choose from. You can write your quantum algorithm and execute it on the simulator. I'd urge you to start with problems with fairly small numbers. If you want to factorize things and express them as a product of prime numbers, it would be good to start with a number in the low 2 digits if you're simulating this on a laptop. The best thing about the library is it does give an implementation of some of the most important algorithms. We don't really have time to go over how Shor's algorithm works in detail, but if you're curious afterwards, this might be a good place for a Go developer to learn about what that is. Now, here is some Go code simulating qubits. Yeah, here's a slide with Go on it. Now, on the right, there is a simple circuit diagram. This shows 2 qubits labeled Q0 and Q1. On our circuit diagram, the first qubit, or Q0, goes into what's called a Hadamard gate, which is a unary quantum logic gate. And then both qubits go into what's called a C-NOT gate, or a controlled NOT gate. And then they both get measured, which is what's implied by that little picture of a speedometer. And what our algorithm is doing is it's entangling 2 qubits together. So we start off by initializing our 2 qubits. We apply a Hadamard gate as we decided to when we drew our circuit diagram. What we see here is the Hadamard gate essentially setting this qubit to a superposition where both possible outcomes when it's measured are equally likely. We then entangle the 2 qubits together with our C0 gate. And what this effectively means is, if we measure the system, we either get 0, 0 or 1, 1. And that's because the entanglement of the qubits has meant that when we measure one of them, it sets the other one to the same value. So when we then measure the second one, it has to have the same value as the first. And you can run this several times, and you'll get different outputs every time. Incidentally, if this was running on real quantum hardware, the effect of the Hadamard gate is to produce a true random number generator, essentially, which has its own implications for encryption, but that's another talk for another day. Now, having taken a look at some actual Go code and seen how you can simulate quantum computers in Go, let's see what happens when you run it. So when you run it on a laptop, it takes a little bit longer than this. I've sped it up, but here we see it's running the Hadamard gate, controlled NOT gate, and then when we get a readout from our system, you always get either 2 zeros or 2 ones. So in this case, we've got 0, 0 with a probability of 1. So that's what happened when we ran it. Now you've got everything you need to go and run a quantum algorithm on a laptop. And there are a couple of algorithms that you should probably know about. One is called Shor's algorithm. Shor's algorithm is for factorizing a number and expressing it as a product of 2 primes. And this has implications for RSA encryption and for elliptic curve cryptography. Grover's algorithm is another one that you should know about if you're studying crypto stuff. It searches through an unsorted data set or solves any problem that can be framed as searching through an unsorted data set. And it has implications for anything involving hashing. Grover's algorithm starts by... Oh, thank you very much. So, Grover's algorithm searches through an unsorted data set. It starts by putting the system of qubits into a superposition of all possible solutions. It marks a particular solution which meets its search criterion using what's called an oracle function, and then it applies amplitude amplification to make sure that that particular solution is the one that's most likely to be output. So it's essentially achieving searching through an unsorted data set. But instead of running in O(n) time, it runs in O root n time. So it takes the square root of the number of steps that it would have done to search through an unsorted data set on classical architecture. How to learn quantum algorithms. If you would like to learn more about that, we haven't been able to go through the code step by step for the things that I've described, but using a simulator like the one in Go is a really good way of getting to the bottom of how Shor's algorithm and Grover's algorithm work. And if you would like to run them in real life, you can, probably not with very large prime numbers involved, but if you want to run some samples, you can run them on the IBM quantum computers or on any of the other quantum offerings that we've talked about. Now that we surveyed the basics of quantum computing, let's take a look at post-quantum cryptography. Overall, quantum computers are getting better. They have implications for encryption. It doesn't mean none of our encryption works. There are different implications for public key cryptography, symmetric cryptography, things like the way we do password hashing. These are all things where the implications of quantum computing are different, and we're going to go through that. There's a group called NIST, who are a standards body, who, as I say, published their post-quantum cryptography standards earlier in the week. This is the end of a long process in which they've been taking feedback from mathematicians, tweaking things, and we've now got this standard. And the post-quantum cryptography is being introduced to Go, characteristically, slowly and cautiously, partly because it was a draft standard that was being implemented, so there was a certain amount of caution about what we had to the public API of the language, what we can't commit to staying the same, if you see what I mean by that. So, like a lot of features added to Go, it's being done slowly and with a lot of discussion, but we're starting with the TLS package in Go 123. In terms of the current uptake of PQC, it's been added to Go 123, as I say. It's been added to Google Chrome, now speaks post-quantum. In fact, so does the Google homepage. We'll talk more about that later. Cloudflare have been using post-quantum cryptography for kind of a while now. There are some SSL implementations that use it, not for the certificates, but for the actual encryption of the communication. And messaging apps, Signal, were the first to start using post-quantum cryptography, WhatsApp messages, and most recently iMessages. If you use that service, you're now using PQC. Now, this has different implications for different areas of encryption. Certificate forgery, for example. The certificate systems that we often use now are vulnerable to Shor's algorithm on quantum computers, but when it comes to certificates, you need a really good quantum computer now to impersonate somebody now. And we don't really have one of those yet, so this is an area that can wait for a while. Symmetric key cryptography, things like AES, there are some implications for quantum computing, but in terms of complexity theory, the speed up's not that much. There's more to be said about this. It might not actually be necessary, but depending on the security level you're targeting, one common perspective is simply increasing the key size used with AES. It solves any problems in this area for now, so it's not really something we need to worry about. Hashing algorithms, again, it's easy to see how Grover's algorithm could impact the security, but in terms of the time complexity of breaking a hash using a quantum computer, the speed up isn't that great. So to find the original pre-image takes the square root of the number of steps that it would on classical architecture. That's not very significant. Finding hash collisions, there's no real improvement. So although Grover's algorithm gives a speed up, it's not as much as you think, and if you're that worried about it, you can switch from SHA-256 to SHA-512 if you want to get the same level of security against quantum computer attacks. So this is very much an area where we don't really need any new cryptography now. It's also worth noting, depending on what you're hashing, it may be the case that passwords that we hash today wouldn't be very useful to anyone in 10 years' time, so we don't have to worry about that. So to cut a long story short, these first three things can wait. Public key cryptography and key encapsulation mechanisms, on the other hand, there is this thing called the store-now-decrypt-later threat model. So this is the idea that if an attacker intercepts and stores HTTP communication inclusive of the TLS handshake and then revisits it in years to come when better code-breaking technology becomes available, then the encryption could be broken and your traffic could be read retrospectively. We don't really know what we mean by later. You'll hear people saying such quantum computers are 10 years away. You'll hear other people saying 30 years. We're not really sure. This doesn't really have the same predictability as Moore's law once gave us with silicon chips, for example. It's quite hard to know when a quantum computer that's actually practical for cryptanalysis will arrive. But this store-now-decrypt-later threat model is essentially the answer to the question of why is this being added to Go now? there may be some data that you're communicating that you don't care if somebody can read it in years to come. There may be other things that you wish to communicate which need to stay secret for a long time. But this is why the rollout of post-quantum cryptography is happening before we've got very good quantum computers. And it's a commonly asked question. Now, public key cryptography that we usually use involves RSA, which is about big prime numbers and multiplying them together, and elliptic curves, which are little squiggles that are that shape. Both of these are vulnerable to Shor's algorithm running on quantum computers. Shor's algorithm gives a very significant speed up. So there's this concept of what's called a bounded error quantum polynomial time complexity that basically means it runs faster on a quantum computer. So the public key cryptography that we use is often used for key encapsulation mechanisms. And this is an area where improvements are being made now to cryptographic standards and to the implementation in Go. So, quick reminder on what a key encapsulation mechanism is. A KEM is a system where you use public key cryptography, symbolized by those little lever tumbler keys, to communicate a shared secret, which can then be a symmetric key, symbolized by the little blue 2-pin tumbler key thing. So, basically, the situation is we don't want to encrypt all our HTTPS traffic with something like elliptic curve cryptography. It's far too computationally expensive. What we can communicate using the public key cryptography is a little AES key, which is a symmetric key. Once that shared secret's been established between a browser and a web server, they can then use this AES key, which was communicated in secret, to symmetrically encrypt and decrypt traffic. So this is what's going on in a TLS handshake. In order to reduce the number of round trips in TLS 1.3, there's a lot of other stuff in the client hello as well. Multiple steps of communication are being compressed down to a single round trip, but this is what key encapsulation mechanisms are. Now, we've mentioned that one way of doing this is to use RSA or elliptic curve cryptography. There is another system which is going to come to the rescue, which is called lattice-based cryptography. This is an alternative to ECDHA or to RSA. It's based on a class of linear algebra problems called learning with errors, which, much like quantum mechanics, is all about little arrows. So, lattice, there's a two-dimensional lattice on the screen to explain what we mean by lattice, but it turns out if you're into linear algebra, you can have loads of dimensions if you want. And learning with errors problem and another system called the shortest vector problem are two different, what you might call trapdoor functions. So in much the same way as it's easier to multiply two prime numbers together than it is to take a large number and work out what the two prime factors were. In the field of linear algebra, there's this learning with errors problem, which is where you get a big linear algebra system, a list of equations, polynomial equations. You then add what's called error, which is getting the answer slightly wrong. And if you know what the original equations were, it's much quicker to work out the answer than it is to essentially take a public key and work out what the private key must have been. So this is a learning with errors trapdoor function in lattice-based cryptography. This is secure against code-breaking attacks on quantum computers, so we don't have a thing like Shor's algorithm or Grover's algorithm, where having a quantum computer is any particular advantage if you're trying to break encryption when it uses lattice-based cryptography. Although lattice-based crypto has been known about for a while, has been avoided in the past because it's more computationally expensive to do the encryption. So if you have a device running a browser, it's got to do a little bit more work to do the encryption. There are bigger key sizes involved, for example. And when it comes to how we decide what lattice-based cryptography to use, there is an American body called the National Institute of Standards and Technology. In the 1990s, this body chose the best elliptic curves that were recommended as a standard. For much of the last 20 years, we've been using elliptic curve cryptography based on their standards. There's been this lengthy multi-year process to narrow down different kinds of post-quantum cryptography and decide which ones to recommend. And they created, amongst other things, Kyber 768, which is a standard for PQC. You'll also see it called ML-Chem 768 because somewhere through the standards recommendation process the name was changed. Thank you. Now, hybrid encryption means using classical public key cryptography and post-quantum cryptography at the same time. There's a gentleman called Bas Vesterman from Cloudflare, and he's a mathematician and software engineer at Cloudflare, and his colleague, Dr. De Sebilia of the University of Waterloo, Ontario, who've come up with a hybrid standard called Kyber X25519 Kyber 768 draft 00, which, now this tells us a couple of things, one of which is that cryptographers don't care much for branding. Another is the X25519 part refers to an elliptic curve. So there's a layer of elliptic curve cryptography. This is a standard that's been used for many years. We know it, we trust it. If there was a problem with it, we would probably know by now. The Kyber 768 bit is the lattice-based cryptography. So that's the layer of post-quantum encryption that's been added to this standard, and draft 00 refers to the fact that the Kyber 768 implementation is based on the draft spec that came out a little over a year ago from NIST. This has been used initially by Cloudflare for back-end development. So if you have, if you're using something like a Cloudflare edge caching server, communication between that and the web server was, I think, the first thing to be encrypted using X25519 Kyber 768 draft 00. If we take a look at google.com and a recent version of Chrome, using the dev tools, we can zoom in on the Cypher suite. So you right click, go inspect, click on the little security tab up there, and that word says security, and have a look at the Cypher suite that's being used, and we see X25519 Kyber 768 draft 00. This shows that the web server and the browser both speak post-quantum cryptography. If the browser were not an up-to-date version of Chrome, or it now works in Firefox as well and other browsers, but if it weren't up to date, then classical elliptic curve cryptography would have been used instead. The website wouldn't rate. But what we can see from this is that the communication between the browser and the web server, when they were communicating the AES key, which is that, they did so using hybrid, post-quantum, and traditional encryption. Now, the point of this is, if you use the hybrid system, an attacker would need a quantum computer good enough to break the elliptic curve component, and for there to be some problem with Kyber that we don't know about yet. And both of these things would have to be true in order for anybody in the future intercepting this traffic to be able to examine the TLS handshake, work out what the AES key was, and then use that to decrypt our HTTPS traffic. This comes with some computational expense in the TLS handshake. The ECDHE component's just 32 bytes in size, so during the handshake, 32 bytes worth of elliptic curve type stuff gets sent, along with over a kilobyte of Kyber public key going over the wire. So that's essentially why lattice-based cryptography wasn't perhaps practical in years past, because the browser's got to do a little bit more computation, basically. What's new in Go 123 is an X25519 Kyber 768 draft 00 hybrid elliptic curve PQC Encapsulation Mechanism. This lives in the TLS package. The use of the new cyber suite is enabled by default. So if you've written a web server in Go, you upgrade to 123. If you haven't specified what encryption to use, it will start using post-quantum cryptography now. You can set config.curve preferences if you want. If it's set to nil, you get hybrid PQC. If you don't want this behavior for some reason, you can disable it with the Go debug environment variable by setting TLS Kyber equals 0. In practice, there probably isn't a reason for you to do that. So this was added to Go from a different GitHub repository, which belonged to a lovely chap called Filippo Valsorda. He's a cryptography engineer, formerly the lead of the Go security team, and the library in question is called the MLChem 768 library. That's another word for Kyber. It got renamed at some point during the approvals process. So this has been taken from this GitHub repo, ported into Go, and in fact, the integration of the library into Go was actually live streamed. I shouldn't think any of you spent 3 hours watching the integration, but I did. Thank you for that, Filippo. So, in terms of integration details, the new Cypher suite is unexported. As you can see from the little x that's not a capital X, what that means is, by the way, this code comes from Go 123 RC2. I believe the line numbers are different in the release candidate than they are in Go 123.0, but the relevant parts of the code hasn't changed. There were some changes to the crypto package at the last minute that were released in 123.0, but not anything to do with post-quantum encryption. So, it's been a hell of a week. So, this may be one of the defaults, but you only get X25519 Kyber 768 draft 00 if you don't specify curve preferences. There is a function called tls.default curve preferences. It's an unexported function. It will return the Cypher suite amongst others. And by the way, the word curve is being used pretty loosely here. Might need a bit of a rethink at some point, but back when the default Cypher suites were all elliptic curve cryptography, the name of them was, it was decided that they should all be called curves and have curve IDs, and then this one comes along where part of it's curvy and part of it's not. So, how are we doing for time? Okay, not too bad. So, in terms of Caddy, so this is the reverse proxy. You can use a thing a bit like Nginx and Apache. It's written in Go. It doesn't use Go's default curves. I did try compiling Caddy with Go 123 release candidate number 2. It doesn't do post-quantum cryptography when you do that. You can specify your own curves, but Go 123's hybrid curve is curve in inverted commas is unexported. So there's no way for you, as far as I can tell, to get the current version of Caddy to work with PQC. To solve this problem, actually not recently, but I think last year, Dr. Vesterbarn, whom we talked about earlier, has forked the Go runtime and created Cloudflare's own version of Go, which has, amongst other things, capital X 25519 Kyber 768 draft 00 Cypher suite. So that means that if you take Cloudflare's fork of Go, use it, get the source code of Caddy, use it to compile Caddy, then you can create a version of Caddy which can essentially be used to host any website, and it will use PQC. And Cloudflare have been doing that for kind of a while. Not initially big communication between Cloudflare and a browser, but communication between Caddy and a back-end web server. This has been in use for a while now, so it is certainly production ready. Cloudflare have a really good blog post about this, and that also studies the uptake of post-quantum cryptography and estimates the number of the number of TLS handshakes there are going on in the world and how many of them use which cipher suite. It's a really entertaining read. So if we use the new feature by writing a simple web server in Go 123, excuse me. Let's take a look at the new feature by writing a simple web server in Go 123. We've written a quick HTTP handle func, which prints hello world. Here I just used some self-signed certificates here and had it listen on a particular port number. And you'll notice that I haven't specified which elliptic curve preferences I want to use. We run this with Go 123 and take a look in our browser. Again, inspect, developer tools, security, have a look at the cipher suite, and it says that the AES cipher was encrypted, the AES symmetric key was encrypted using X25519 Kyber 768 draft 00. So we can see that the Go implementation is now working and that it's secure, and that it's securely using post-quantum cryptography and traditional cryptography hybrid system. Now, the NIST approval update, which happened on Tuesday, and occasioned a frantic rewrite. So this standard was finalized 3 days ago. It's important to understand that the current implementation in Go is of equal security to the finalized version of the standard. There will most likely be a tweak to one of the internal implementation details. Wasn't quite brave enough to open a pull request, but I did have a go at making the necessary changes locally, and whether I did it correctly or not, we will never know. But for me, it was a one-line change to the TLS package to implement the finalized version of the standard. If we had an implementation which offers multiple different security levels, so Kyber 768 and Kyber 1024, and if all of those security levels were all reusing the same random seed, then the updated version of the standard would offer a better level of security than older implementations. Go only implemented Kyber 768 only, so there have been some changes to the cryptographic standards recommendations, but the implementation in Go offers the same level of security as the new version of the standard. You can and should upgrade to Go 123 to use the latest version of the TLS package. And I'd just like to take a moment to thank a number of people who are cleverer than me, including Dr. Vesterbein himself, for helping me make sure that that's true. Now, possible future developments. To take a look at, how are we doing for time? To take a look at possible future developments. So the NIST Standards finalization will, in the short term, create an increased uptake in use of post-quantum cryptography. We may also end up dropping the 00 or the draft 00 part to make the name of the cipher suite faster to say when you're doing a talk. Another thing that's likely to happen in the future is implementations that are out there now of the draft version of the suite could be upgraded to reflect the changes made after the recent NIST publication. So that's, if we were to guess at what might change in Go 124, that's one possible area where people might decide that there's going to be a slight change there. I can't speak for the Go team myself, but it's certainly a thing that they could do if they wanted to. So functionality in the TLS package could be exported in future, possibly with a different curve name. This would, either this change directly or some alteration to Caddy in the future might mean that we're able to use PQC with Caddy. It's another thing that might happen soon. There are cryptographers who feel that the use of so-called hybrid systems where using PQC and traditional encryption as a sort of interim measure, largely because we know a lot about elliptic curves. We've been using them for a long time. They work. Kyber, on the other hand, feels a little bit more experimental or newer. there may come a time when people decide that we're just going to use what by then everybody will probably be calling ML-Chem or Kyber as public key cryptography means for key encapsulation mechanisms. So we might drop the use of elliptic curves one day. Another thing that could potentially happen in the future is changes to the way we do certificates for HTTPS certs, SSL certificates as well. Again, this wasn't as urgent because in order to assume somebody else's digital identity now, you would need a better quantum computer now than is available. So there are things like symmetric cryptography, key sizes, choice of hashing algorithms, which could be changed in future. And one of the NIST standards was the one that we've talked about, which is the one everybody is using. There were 2 other publications from NIST at the same time that were to do with means of digital signing. So those are other areas where the standards body's now got a mature standard that could be implemented in programming languages in future, potentially. Yeah. Managed to finish on time, well, okay. Thank you very much, everybody, for your time and attention. Thank you very much for coming along. It was a great turnout. So there are links to the slides that will be going on this blog at some time soon. You can follow me on social media if you want to. But I will make sure that, excuse me, I will make sure that when the video is available, I'll put a link to that up on the website as well. Now, do we have time for questions? Probably
yeah, one or two.
Who's got the most burning question?
Hi, thanks for the great talk, really appreciated. I was just wondering, why does X25519 Kyber 768 draft 00, I don't know how you kept a straight face while saying that, use both elliptic curves and lattice-based crypto? Is it just trust in elliptic curves? Or
yeah, I think because the Kyber standard was still in draft at the time it was implemented, there was still a consultation process going on where cryptographers and mathematicians were writing to NIST with any recent research. There was a feeling that although we do need post-quantum cryptography, what we also need is not to be using a shiny new thing with the word draft in its name as the only means of encrypting HTTPS traffic. So the reason was just because elliptic curves are tried and tested and we've been using them for a long time, and that's why people felt comfortable using the experimental stuff if it's just one layer and there's another layer that we know works.
Okay, cool, thank you.
I think we need to clear the room now, don't we?
All right, massive hand for Sam Burns, everyone. Thank you.